Welcome back. We'll continue our study of electric fields by talking about electric flux. Electric flux, in short, means how much electrical field is passing through some given area. In black, here we have some area viewed from the side, and the red arrow here is the electric field at this point. We also have another vector here. This is called the A. It's perpendicular to the area that we are investigating, and its magnitude is the actual value of the area. In general case, there's an angle between these two directions called theta. The electric flux is denoted by Greek letter capital phi, and it is the product of the electric field and the area, and in fact we want the component of the electric field that is parallel to the vector A. So this piece here, which is E perpendicular to the surface parallel to the A, like this, and the parallel component is get by multiplying by cosine theta, as we can see from the figure. Mathematically, this can be expressed as the dot product between the vectors E and A, and let's call this phi E the electric flux. Usually the area that we are investigating, or the surface we are investigating, is not a flat plate like this, but it can be of any random shape. And be something like this. When we want to calculate the electric flux through the whole surface, we have to divide this surface into small elements. We can make them really small. Let's make one more here. So it has the vector A, but because this is infinitesimally small, instead of calling it A, we call it dA. So it's a very small surface element. And then there's some kind of a electric field going through at that point on the surface. And let's call this EI, some numbering. And this would be DAI. Because we have a lot of these little surfaces, we just keep track of them by numbering them individually. So the total flux, by calculating this way, would be E total would be the sum of all the fluxes of these individual area elements. So we have EI times, or taking a dot product with this DAI. And as you have seen before, when the area element becomes really small, we have infinite number of them, the sum will be replaced by integral. So we are integrating over the whole surface. And that's why we have this circle here. This means surface integral. So we investigate every little piece on the surface called dA, and we dot product that vector by whatever happens to be the electric field at that point. And this is the actual mathematical formulation of electric flux. You can see that calculating this integral becomes tedious if the surface is very irregular. And in fact, we only bother calculating this when we have some kind of symmetry that makes our life easier. As an example of such a symmetry, let's consider a sphere. This is drawn in 2D, but it's supposed to be a three-dimensional sphere. And we have a positive charge Q in there. The color of positive is red. So Q. And this creates an electric field that is radially outward to all directions. And luckily for us, the electric field at any given point is perpendicular to the surface. So instead of this, we can use the simpler form QE equals the perpendicular component to the surface, which in this case is just the magnitude of the electric field at this surface, which is some distance r away from the surface. Because this is symmetric, the value of E is same everywhere on this surface, on this sphere, and that's its constant called E. And then we have only left the area of the sphere. And we know that the expression for that is 4 pi r squared. So this would be the total electric flux through a sphere that has charge Q contained inside. We will use this method of calculating the electric flux all the time when we are applying the Gauss's law, which will be the topic of our next video. Before moving on, however, it's worth noting that the flux can be either negative or positive. For example, let's have another surface here. We have some electric field line, just one going through. Here's the electric field at that point, and here is the electric field when the flux is coming in. And then we have the surface vectors. Now let's do this again. So let's assume it's perpendicular, right? And here the area vector would be in this direction. So A, and E, and also here B. Now, if we calculate the flux in these two cases, on the outgoing side we have phi e to be E dot A, which is E times A times the cosine of the angle between them, which in this case is 0. So we get E times A. On this side, however, we get E times A times the cosine of the angle, which is now 180 degrees, which is, this one is -1, so we get minus EA. So we see when the flux is going through the surface or out of the surface, it's positive, and incoming flux will be negative.